Good morning, good afternoon, good evening, good day, and good night, wherever you might be. Mathematicians of the world, welcome to the Banach Center. We hold a meeting in a brand new lecture hall, which you will see after I pass the floor to Alain. Let me just say that it was custom built for the new era of hybrid conferences. So that if you ever want to have a conference with, say, 100 people on site and another 200 people on Zoom, it might be one of the best places in the world, equipped and designed for this purpose. And it is my great honor and pleasure to introduce our speaker, Alain. Actually, he needs no introduction, but since there are so many young students in the audience, some of them as young as second year undergraduate, I have to say a few words. Of course, it's impossible to summarize lifelong creativity, ingenuity, and achievements of Alain. But let me just mention some key facts. One of them is actually very much related to this place, to the Institute, because Alain got his Fields Medal for classification of factors in 1982, and it was the Congress in Warsaw organized by the Institute of Mathematics of the Polish Academy of Sciences, which is us. So we are very happy about it, of course. And at around the same time, 1980, Alain discovered non-commutative geometry. This is a brand new topic subject area of mathematics, field of research, which is very rich and diverse with lots of applications all over the place, from solid state physics to number theory. And of course, I know I'm biased, but I find non-commutative geometry extremely beautiful in its own sake. And one of the key applications is the application of non-commutative geometry to physics. And Alain will now tell us about some very fundamentals of non-commutative geometry and how we can apply it. So without any further ado, Messieurs, Dames, Alain Cohn. Alain, the floor is yours.
Thank you. Thanks a lot for the introduction. So, I mean, I'm going to give, a kind of overall introduction to non-commutative geometry. And what I have chosen to do, I mean, there will be two talks, 45 minutes each. So what I have chosen to do is first to give a kind of historical perspective, if you want, on, I mean, the way I was led to this topic, and especially on the role of quantum mechanics and of von Neumann factors and of foliations in the early days of non-commutative geometry. And I mean, in the second part, I will introduce one of the main tools of the theory, which is the quantized calculus. So, I mean, what I hope is that, I mean, these talks, which are introductory talks, will serve, if you want, as a way to understand better a talk which I gave a few days ago about the notion of space. So here I really want to give you from the start what I believe to be the root of the theory. And I mean, as I often repeat, but I insist on that. I think the root of the theory is coming from physics, and it's coming from the message that we receive from distant parts of the universe, which is spectral. So in a sense, I mean, this began by the understanding that when you look at spectra, coming, for instance, from the light of the sun and so on, they contain an information which is very non-trivial and which manifests itself in spectral lines, which are missing lines in first the visible light when you look at it like this. And I mean, these spectral lines turn out to have a lot of structure. And I mean, it took a long time in order to decipher this structure. At first, what was understood is that there were, I mean, parts of these lines which were like the signatures of chemical elements. And this was obtained by transforming these absorption spectra, like the one I just showed you, into emission spectra by considering chemicals and warming them up, like if you take sodium, for instance, and then finding out that what you get are emission spectra, but which correspond one-to-one to some lines of the absorption spectra coming from the sun, for instance. And so, I mean, what we receive from the universe are like barcodes, really. I mean, this is the way I like to think about it. But what turned out to be the case was that by deciphering these barcodes, this was the real beginning, if you want, of quantum mechanics, and also I would say of non-commutative geometry, if one wants to go sufficiently far back. And this was done by the following understanding, which is done by Werner Heisenberg. So, but it's the understanding of a law which was found by physicists. And this law was that when you input, if you want, this spectra, the spectrum of a pure chemical, when you look at it at the frequency level, then what you find out is that the lines shouldn't be parameterized by a single index. They should be parameterized by a pair of indices. And what is amazing is that the lines don't form a group, but what happens is that if you index them by pairs, like ij, if you want, then the line which is indexed by ij and the line which is indexed by jk combine together to the line which is indexed by ik, and the corresponding frequencies actually add up. And the thinking of Heisenberg, which was, if you want, amazing at his time, and it amazed, in fact, Dirac, who was a student with him, which Heisenberg did in Helgoland when he was taking refuge there. I mean, he was sent there because he had the hay fever. And he was housed by an old lady. And he had this idea that somehow the physical quantities, the physical observables, should be, if you want, obtained from really what is observed. And from that, he had the idea that he had built, if you want, a kind of system in which somehow he was inputting the Ritz-Rydberg combination law to define the product. And what Heisenberg was brooding about at some point during the night, he was trying to prove, I will explain how, he was trying to prove that in his system, the energy was conserved. So, I mean, it was late, it was already in the early morning of the next day, and he was doing calculations, and he was so excited that he was constantly making arithmetic mistakes. But around 4 o'clock in the morning, he found that, okay, everything was working beautifully. In fact, what Heisenberg had verified, if you want, is that when you take the Hamiltonian itself, H, it is invariant under the time evolution. So, I mean, what Heisenberg did actually, he built out of the Ritz-Rydberg combination principle, he built matrices. He didn't know what matrices were about, were known to mathematicians and so on. He didn't know that at all. But he had the idea of if you want, he knew that in classical mechanics, you can use the action angle variables and you can do Fourier transform. So if you had a group, you could, if you want, do the convolution. And he did the convolution corresponding to the groupoid, which was underlying the Ritz-Rydberg law. And that way, I mean, to me, this is really, you know, the discovery of non-commutativity in physics. It is a discovery of an absolutely crucial fact, which is that when you take physical quantities, if you want, when you manipulate the observable quantities for a microscopic system, the order of the terms when you manipulate these quantities cannot be ignored. You have to pay attention to the order of the terms. And so what it means is that if you look at standard algebra, if you want, where you take the Cartesian coordinates, and of course you do usual algebra, which is commutative, this does not hold in the algebra of coordinates on the phase space of a microscopic system. So, I mean, this is a tremendous discovery. And I mean, this discovery was very soon formalized, if you want, or formulated mathematically. I mean, Born and Jordan understood, of course, that Werner Heisenberg was using matrices. But then gradually, also thanks to the Schrodinger equation, to the equivalence of the Schrodinger point of view and the Heisenberg point of view, it was found, if you want, by von Neumann, what was the sort of correct formalism for the discovery of Heisenberg. And I mean, this new formalism, which is totally new, if you want, has the following property. So this is, if you want, the evolution of observables according to the Heisenberg law. And now, if you want, in this new formalism, the fundamental change is already taking place for what is the notion of a real variable. I mean, we all believe that, you know, we know what is a real variable. And when we are asked what it is, okay, we say, well, I have a set X and I have a map from X to the reals. You know, but I mean, it turns out that quantum mechanics tells us that there is a much more fundamental variability which is taking place, and that the correct notion of variable is not that one. This is a classical notion. The correct notion of a variable is that of a self-adjoint operator in Hilbert space. And when you think about it, I mean, if you know a little bit these operators, you will find out that it's perfectly coherent for lots of reasons. One of these reasons is that if you take a self-adjoint operator in Hilbert space, very surprisingly, even if it's not bounded, you can take this operator and you can apply to this operator any measurable function. And what happens also is that if you take ordinary real variables, that the way we think of them classically, well, they have exactly the right, I mean, the self-adjoint operators have exactly the properties that you would expect. Namely, the range of a variable is the spectrum of the operator. The number of times the real number is reached as the value of the variable is the spectral multiplicity, and so on and so forth. I mean, there are many, as we shall see, I mean, you know, there are many properties which in fact become somehow much more significant when they are taken for operators. And at the time of the beginning of quantum mechanics, I mean, you know, physicists were very aware of this, and they had an intuitive idea about these variables, and they were calling them Q numbers. I mean, I think it's Dirac who said, you know, that after the discovery of Heisenberg, it was easy for a mediocre physicist to write a great paper. So I mean, I don't know what he meant for before Heisenberg, but somehow, if you want, the discovery of this formalism opened a completely new world, and so there is, and what the genius of Dirac, I mean, what Dirac found, I mean, Dirac in a paper, it is really the first paper on quantum, I mean, it's on the quantization of electrodynamics and quantum electrodynamics. And the idea of Dirac was the following: if you think of the analog of complex variables or Q numbers, I mean, to be operators which are not necessarily self-adjoint, what Dirac found is that if you look at the commutation relation, which is A star minus A star A is equal to 1, then somehow, you know, this relation immediately implies that when you look at the absolute value square of A, which I will call like A star, okay, I mean, then the spectrum of A star is formed of the integers. And I mean, the reason is quite easy to understand. The reason is that if you know, it's known in operator theory that if you take two operators A and B, you have that the spectrum of AB is equal to the spectrum of BA, except possibly for 0. So I put a star here because I exclude 0. So if you have this condition, what happens is that, of course, A star is positive, so the spectrum has to be positive. And if I take an element in the spectrum, because of this relation, I can move it down by 1. Okay? And I mean, if I want it to be positive, when I move it down by 1, I have to hit 0 at some point. Otherwise, I would make it negative. So it has to be a positive integer. Now, what Dirac did is, I mean, he knew from Einstein and Planck that in the electromagnetic field, you want to have photons. So you want to have an integer number of them. And so you have to have that the coefficients in the waves have to be quantized so that the absolute value square should be an integer. So he did that. And out of that, he could compute explicitly the coefficients A and B of Einstein of emission and absorptions of photons. And for that, Dirac was working at some fixed temperature. He was not working at 0 temperature. And for that, he was using, if you want, an ansatz, which is going back to Boltzmann and Gibbs, but which is giving you the equilibrium state at temperature, at absolute temperature T. So when you look at a quantum system at equilibrium, at temperature T, an equilibrium state will be, if you want, of the following form. It will be given by the trace, the operator trace, of the product of the observable A by the exponential of minus beta h. Beta is the inverse absolute temperature, and K is the Boltzmann constant. Of course, there is a normalization constant, which is Z here. And so if you want, we have seen two equations. I don't want to put too many equations. I just want to show you very few equations, in fact. So what we have seen are two equations. We have seen this one. This is the evolution of observables from Heisenberg, okay, which of course has a semi-classical limit, which is ordinary, Poisson bracket with Hamiltonian. But I mean, this is really much simpler because it's just, operators, and there is no Poisson bracket of any kind. And also we have seen this Gibbs-Boltzmann equilibrium state. Now, it turned out that Murray and von Neumann went much further than, if you want, the general formalism invented by von Neumann, in that what they did was to investigate subsystems. That's really the idea, which is, if you want, behind their work. And at first, they tried to understand a subsystem of a quantum system by saying that, well, it should come from a factorization of the Hilbert space, namely the Hilbert space H, okay, where normally you take all operators because you are dealing with quantum mechanics. There, you would like to take only the operators which act only in one of them. And I mean, what they write in their paper is the following. They write that, so this is their paper on factors. So what they say is that interpretation of what they are doing is suggested by quantum mechanics. So instead of taking in quantum mechanics all operators in Hilbert space, what you want is to take the observable quantities which happen, if you want, which occur in a subsystem. And when doing that, Murray and von Neumann had a fantastic surprise. Namely, after formulating abstractly what were the properties that should be satisfied by a subsystem, they discovered that there were factorizations, so they call them factor. This is the origin of the name factor. So there were factorizations that actually were not corresponding to the fact that you would take the Hilbert space and you would write it as a tensor square. Okay, I mean, I write tensor square because all Hilbert space, infinite dimensional, are the same. Now, so this is what they write here. This is what they write. And what they write in particular, which is in fact more striking, and they say the fact that this ansatz of writing the Hilbert space as tensor product is not true is therefore the more remarkable, particularly so because certain features of the exceptional rings seem to make them even better suited for quantum mechanical purposes than the customary full system, if you want. Now, so what happened more precisely is that what Murray and von Neumann found, they found that there were three types of factorizations. So the first is type one, it is the boring one. It is, if you want, the idea that you factorize the Hilbert space into a tensor product. Then the second one for them was really the most surprising. It's called type two. And the reason why it was amazing to them was that in this type two situation, you can, if you want, you can do the same job as what you would do if you would classify the subspace of Hilbert spaces. But now what you find is that instead of these subspaces to be classified just by an integer, which might be infinity, what you find out is that they are classified by real numbers. And I mean, in the type 2 one is when they are classified by real numbers from 0 to 1, and the type 2 infinity from 0 to infinity. So they discovered continuous dimensions, and of course, I mean, you know, this was a tremendous discovery. And then, okay, they found out that there were other factors which were not either type 1 or type 2, and okay, this is what they call type 3. And essentially, it's all that remains. I mean, one thing you can remember about type 3 factors is that, you know, the type 3 factor has only one representation. If you try to represent it differently in different inverse space, they are all, in fact, isomorphic. This is characterizing the type 3. Okay, so, I mean, around 1967, in fact, physicists, there was Huguenots and Winning. I mean, in fact, what they found out is that they defined a condition, a mathematical condition, which they call the Kubo-Martin-Schwinger condition, because it had roots which were older. And what they found out, if you want, is that there was a mathematical way to write down the relation that exists between the Gibbs-Boltzmann equilibrium states that I have defined before, okay, and the evolution as given by Heisenberg, by the Heisenberg equation. And I mean, the way they wrote it down was that it's, okay, I mean, you see, what is going on really is that there is, in the two formulas, there is the same ingredient, which is this h and the exponential. But what is different is that in the sigma t, you have it as a coefficient in the exponential of h, whereas in the Boltzmann, you have minus beta as a coefficient of the h. And I mean, this, of course, rings like analytic continuation and so on. And this is what Huguenots and Winning did. I mean, they formulated the fact that the trace property entails, in fact, a way to permute when you take the state evaluated on AB and the state evaluated on BA, a way to permute and to obtain a relation between the two. And this is a KMS. This is a KMS condition. Now, in 1970, in fact, I mean, so the birthday was just a year ago, the 50th birthday. Tomita and Takezaki, I mean, it's really both of them because Tomita developed a general theory, but Takezaki proved that it satisfied the KMS condition. So the main result was that if you take a von Neumann algebra, so von Neumann algebra is a bit more general than a factor, but the factors are von Neumann algebras. And if you take a faithful normal state on this von Neumann algebra, then if you want, there exists a unique one-parameter group which satisfies the KMS condition. So really what is going on is that if you have the Boltzmann-Gibbs state, then you get the Heisenberg evolution. So it goes in that direction. It's well defined. And I mean, I started working on this topic just 50 years ago. And I mean, what I showed in my thesis. So I mean, I showed this in April of '72 actually. So what I showed in my thesis was, in fact, if you want, this one-parameter group of automorphisms was in fact independent of the choice of the state. So it was in fact a fundamental property of the factor of the von Neumann algebra. And the reason was the following. The reason was that when you change the state, in fact, you only change this one-parameter group of automorphisms by inner automorphisms. And when you have a non-commutative algebra in general, there is an exact sequence which tells you that the group of automorphisms of the algebra has a normal subgroup, which is the group of inner automorphisms. So the inner automorphisms are the very trivial automorphisms. They are of the form an element X gives you UX U star, where U is a unitary element in the algebra. So they form a normal subgroup. And as it turns out, if you want, when you divide by this normal subgroup, okay, you obtain the most interesting group associated to the algebra M, which is a group of outer automorphisms. And this group of auto-automorphisms, in fact, has a non-trivial center. And this center, I mean, okay, inside this center, there is this completely canonical time evolution, which is coming from non-commutativity. And the reason it comes from non-commutativity is precisely this Kubo-Martin-Schwinger condition. So after finding this fact, if you want, I published a contribution note, which is in April 72. And then, okay, I understood that the invariants which I had defined before were becoming completely computable. And in fact, I mean, in the spring of 72, in fact, in June 72, I was visiting Erling Stormer in Oslo. And I found a way to reduce the type 3 factor, except for type 3.1. So I had been able to, so I had subdivided this type 3 into type 3 lambda, where lambda belongs to 0, 1. And what I proved in June 72 was that factors of type 3 lambda for lambda different from 1 were written as a cross product of a type 2 by a single automorphism. And in fact, when I went in Bandol in July of 72, so this was in July of 72, I could announce to Bob Powers, I mean, the fact that there were hyperfinite factors which were not infinite tensor products of type 1 factors, thanks to using the work of Wolfgang Krieger. But this was using the invariants. And I mean, among these invariants, I mean, there was a module which was splitting the factors into type 3 lambda for lambda in 0, 1. And there was also the periods. I mean, the periods is a very, very striking invariant in the sense that what it tells you is that for a factor, there are certain times when the factor is static, I mean, when it doesn't move, if you want. And this period group can be, is not necessarily a closed subgroup of R. And I mean, and it was from the start related to an invariant defined by Araki and Woods in their classification of infinite tensor product of type 1 factors. Okay, so at this point, if you want, okay, then I worked, of course, on hyperfinite factors. But then I came back to France and I went to IHES and you know, then I found out that I had a hard time to explain to people who are specialists of many other fields what I had been doing about factors. And then, I mean, by discussions, I mean, in particular with Dennis Sullivan, I found out that in fact, there was a marvelous way to illustrate, at least at the beginning, the theory. And this way was using a notion which is very familiar to geometers, and which is the idea of foliation. Now, what I want to give you, what I am trying to do is to give you, you know, a kind of a short historical survey, but mainly to give you some mental images. And so, I mean, the foliation, you should think of a foliation as a local factorization. So it's very much in the spirit of Murray and von Neumann. So what you have, what does it mean? It means that, you know, you have a full manifold, of course, you have a full manifold, but somehow when you work locally in this big manifold, what you have a way to write it locally as a product. And here, for instance, you know, I would write the manifold as a product of a segment by a two-dimensional piece. Now, for foliation, what happens is that you don't want to retain the fact that elements in this piece are on the same height. No, what you want is to retain the fact that it has been split into plaques like this. Now, these plaques, this splitting into plaques, of small open sets, so it's a local factorization, they fit together. They fit together. And when you move along a plaque, you are moving along a leaf. So in fact, the foliation, what it is really, it is something like that. I mean, it is giving you a kind of, what is going on? Yeah. So you see, so I mean, locally, it looks like a product like this, but not at all globally. So the leaves, even though if you want, they look locally like you have been splitting the manifold into a product, you have been factoring the manifold, when you go along these leaves, I mean, they will come back, and they will come back at different places and so on. And which means, if you want, that when you look at the set of leaves, it's a very interesting space, which, as I will explain very shortly, is not at all the type of space we are used to. But if you think about the constructions of Moraine von Neumann, what is called the Moraine von Neumann, the group measure space construction, then what you find out is that there is a direct way to associate to a foliation von Neumann algebra. And what is this way? So if you have a foliation, then what do? Well, you find out that in general, it's not possible to take functions which are constant along the leaves. It doesn't work. For instance, if you take this foliation of the torus by a rational angle, you find that there are no functions which are constant along the leaves by ergodicity. But what you can find is you can find Q number valued functions. Q number valued functions. And so what are these functions? What does it mean? It means that I will consider what I call random operators associated to the foliations. And what are these random operators? They are a family of operators, one for each leaf. So an operator for each leaf, F, if you want. It's a family. And where are they acting, this operator? Well, the operator T sub F is an operator acting in the Hilbert space L2 of the leaf, in L2 of the leaf. This makes perfectly good sense. Okay, you don't have to define a measure or anything like that, because you can talk about half densities. And then when you take these random operators and you say, well, you have to say that they are bounded, and you have to say that if they are equal almost everywhere, then they are equal. That's it. You get a von Neumann algebra, abstract von Neumann algebra, not even represented in Hilbert space. It's an abstract von Neumann algebra. Now, what was very striking, this was around 76, 77, by discussions with Sullivan and so on, is that the simplest foliations were illustrating the most exotic examples of factors. And so, I mean, of course, this one was illustrating the type 2 infinity hyperfinite factor, so the Kronecker foliation. But in fact, if one looks at a little bit more fancy example, so the little bit more fancy example is the following: is you take the following. You take a Riemann surface of higher genus. Okay, so I mean, so you take a Riemann surface of higher genus, and what you do is you take the unit sphere bundle on this Riemann surface and the geodesic flow. Now, the geodesic flow turns out to have very special properties that, if you want, when you look at I mean, there is a direction which is transverse to the geodesic flow, and in which everything gets closer and closer to the line, I mean, to the geodesic line. And I mean, this defines the foliation, and this foliation can be described quite concretely by uniformizing the Riemann surface. So what you get is the quotient, if you want, of the disk. So the quotient of the disk by a discrete group. And when you look at the sphere bundle, what you get is the quotient of SL2R by the discrete group, which is the fundamental group of this, which is pi1 of this surface, pi1 of sigma. Now, so this is my surface sigma. And then what happens is that the foliation, which is the, if you want, an observed foliation of the geodesic flow, is in fact just the division by the group of upper triangular matrices in SL2R. And I mean, what was amazing is that this example, which is very standard in foliation theory, was giving the hyperfinite factor of type 0. So it was giving a very exotic, very non-trivial factor. And from the start, if you want, it was clear that foliations were a beautiful sort of scenery, in which, if you want, the theory of factors was acquiring a geometric meaning. But, okay, on the other hand, when you have a foliation, you have more structure, because foliation is differential geometry. So from that time on, I began to think on how to use the differential geometry of the foliation to, if you want, together with the fundamental algebra. So first I was doing longitudinal index theory, but in 1980, by studying this very, very specific foliation, which is, if you want, what is called the Kronecker foliation. So you can think of it in a different way. I mean, you can think of it as being the torus. So the torus is obtained by identifying these two, these two sides and these two sides in a square. And the foliation that you get, I mean, the foliation is obtained by taking some line of irrational slope. Okay, so this is the type of foliation that you get. And then I realized that, in fact, okay, there was a way to get an algebra which was much more closely related to the foliation than just the fundamental algebra. If you want, the fundamental algebra of the foliation is just telling you what is the measure theory. So, and the measure theory, I mean, of course, it's very non-trivial and so on, it gives you a lot of things, but you want more. You want the topology, of course, and in fact, you want the differential geometry. Okay, so at first I understood, of course, that the topology was given by a certain C-star algebra, which is associated to the foliation and which is obtained by looking at what is called, if you want, the autonomy groupoid of the foliation. But what was much more interesting was the differential geometry. And the differential geometry is something which I discovered in fact in 1980. And I published a contribution note in 1980, which is called C-star algebras and differential geometry. And in which, if you want, I analyzed the differential geometry that was coming from this foliation, from the foliation from the Kronecker foliation, and with the fundamental idea that while the algebra, so the algebra you can obtain by taking a transversal like this, and by taking functions on transversal, and by taking, if you want, the diffeomorphism that comes back by going along a leaf. So in doing that, you get a cross product. And I mean, this cross product was giving an algebra which was done before, which was the algebra of the irrational rotation, which is called A theta. But what I obtained in my contribution note was quite different from that, because what I did was to give a smooth structure to the C-star algebra. And the smooth structure was coming naturally from the foliation, but at the level of the C-star algebra, it was best defined by looking at the action of a Lie group on the C-star algebra. And I mean, this Lie group in that case was very simple. It was just the two torus. So it was just T2, if you want, which is acting by two derivations. And when you do that, okay, I mean, you have now something which is infinitely better. Why is taking the smooth structure infinitely better? Well, it's infinitely better because normally when you write the elements of the C-star algebra as a sum in Fourier transform of products of the two generators, UN and Vm, where U and V satisfy a commutation, where this is some number of modulus 1 times Vu, what happens is that for the C-star algebra, you cannot say which coefficients you take. But when you take the smooth structure, you find out that the condition for the algebra is exactly that this sequence is of rapid decay. So this makes things infinitely simpler. And what I found in my contribution note is that, I mean, I will give you immediately the translation into English, but I mean, this is the original theorem. So what I proved is that thanks to taking other geodesics from the one you start with, then you get a finite projective module over the algebra, which is the algebra of smooth functions, if you want, on non-commutative torus. But much more is true, because what you find that you can compute the dimension in the sense of Murray and von Neumann, because the algebra is of type 2. So you can compute the dimension of this finite projective module and define the absolute value of P minus Q theta, where theta is irrational and P and Q are integers. So of course, this dimension is in general an irrational number. It's P minus Q theta, okay? But what I found, and I was totally amazed by, is that I could compute the curvature of natural connection on this finite projective module, because the connection, if you want, was given by being coherent with the partial derivatives, which are given by the derivations, delta 1 and delta 2. And when I computed the curvature, I found 1 over theta minus p over q. So then, I mean, it was obvious that if I would take the integral curvature, which is the product of the dimension by the constant curvature, then you get an integer. Now, this integrality was to me really the real start of the whole theory. Why? Because it was telling that even though the original situation could have looked fairly irrational and so on, you know, because of this foliation and so on, no, there was an integrality theorem that was lurking behind. And that was, if you want, combining these two irrationalities to get an integer. So, I mean, what I would say at this point is the following, is that this was just an example. It was just an example of a foliation, of a very specific foliation. But there are, of course, an infinite source of foliations, and each of them has an underlying non-commutative space. And for each of them, one can, you know, try to understand what is going on and develop the theory. And I will finish this first part of my talk by another surprise which happened at around the same time, I mean, at the beginning of the 80s, which was to understand that the other example which I gave you before, which is the example of the Riemann surface of IHES, if you want, and, you know, of the Amosov foliation for such a Riemann surface. Well, it turned out that it was a special case. I mean, could be understood completely in non-commutative terms. And what happens in the non-commutative world was the following. What happens is that you take, if you want, the leaf space. You have to understand that what I was talking about before is really the algebra of the leaf space. The leaf space is a very, very, very tricky space. It's not an ordinary space at all. It's a space which, I mean, if you try to, for instance, inject this space into the real numbers, you cannot do that. You cannot do that explicitly. This is impossible because of ergodicity. So you cannot inject a leaf space, I mean, of course, of a non-trivial foliation, into the real numbers in a measurable way. This is not possible. Now, what happens is that this leaf space then acquires amazing properties. Why? Because of the previous time evolution, which I had found. Okay, so this time evolution now manifests itself at the mathematical level by the fact that foliation, which is not of type 2 like the previous Kronecker foliation, has a time evolution. And it turns out that this time evolution has a very strange compatibility property in the case of codimension 1 with the fundamental class. So there is a fundamental class, as for an ordinary manifold. This fundamental class is not invariant under the time evolution, but its second derivative of the fundamental class vanishes. So this implies, if you want, that you can contract the first derivative, which I call x dot. You can contract this first derivative of the fundamental class by the time evolution itself, okay, which I call I sub h, because it's like contraction with the h of Heisenberg. And then amazingly, you get what is called the Godbian-Weyl invariant. And then, you know, and of course, this connects with the important ideas of Steve Herder. But using that, I was able to show that one invariant that we had defined with Takezaki, which is the flow of weights of factors, will have an invariant measure. So this implied immediately that if the Godbian-Weyl invariant, which is a pure differential geometric stuff, does not vanish, then there would be type 3 for the corresponding factor. So, I mean, this showed from the beginning, I mean, this was in the early 80s, like 83 and so on. So, I mean, this showed from the early beginning, if you want, that there was an amazing landscape of new spaces, of these non-commutative spaces, and that somehow, you know, they would require to adapt all our thinking about differential geometry to this totally new set of examples. I want to end this first part by saying, that a new theory needs two things. I mean, it requires, of course, first, great discovery like the discovery of Heisenberg, of a totally new landscape. But what it requires to have a huge family of new examples. Because if you don't have examples, you can, develop a theory abstractly. Okay, this would be rather boring. And it requires also, I would say, a totally new feature. Now, the new feature, which I hope I have been able to convey, even if, without, of course, spelling details, the new feature of non-commutative spaces is that they are not static, they have a time evolution. This is an amazing fact. And to me, in a way, it made all classical spaces very boring because they were static. So in the second part, so I would stop here for the first part, but in the second part, I will explain to you how, starting from the quantum again, we shall get the fundamental tool, which is a new form of calculus, and which I call the quantized calculus. Okay, thank you. I think I will stop here.
Okay, so let's now, thank you very much. Let's now have some questions. And maybe we will begin with questions from the audience. Are there any questions from the audience?
Yeah, let me stop sharing.
Yes,
for now.
Yes. Okay.
Can you see me? Can you see me in full?
Yep. Yeah, we see you all right. Yes. Okay. Any questions from the audience? Go ahead, Adam.
Yes, so I have a question. Do these type 2 factors appear in physics as a subsystem algebras, or since the time evolution
no,
for them is trivial?
I think if you want, von Neumann was probably thinking about type 2 factors when you wrote this about quantum mechanics. But of course, type 3 occurs everywhere in quantum mechanics. When you take the local theory of Haag-Kastler, the local algebras are all type 3. So if you want, what happens is that if von Neumann was thinking about type 2, he was not right. But we are all never right on the first shot. You have to. But maybe I will try to explain that later. But if you want, the one idea which I have, and which is actually, I will start the next session about with this idea. One idea which I have, in fact, is that if you want, the time is only emergent, and it's emergent because we only have partial knowledge of the quantum, and this partial knowledge means that we are in a subsystem, and this subsystem is type 3, and the time evolution is coming from that. So there was a lot in the idea of von Neumann, for sure. Of course, he didn't know about the time evolution, but.
Okay, thank you.
Anybody else? I don't see any other vote. Yeah.
I have one more question.
Go ahead.
So what is the relation between the von Neumann algebra associated to foliation? So say for example, for a Kronecker foliation and the cross product.
Well, you see,
Morita equivalent or?
Yeah, of course. Yeah. Okay. So what happens? Yes, that's a good question. What happens is that the fact that there is an algebra for the Kronecker foliation immediately implies that the cross products for values of theta, which are transformed into each other by SL to Z, are Morita equivalent. Because indeed, if you want, they all give the same tensor product by the compacts. And so they are Morita equivalent. And in fact, in my contrandu note in 1980, I had constructed the bimodules, which give you the Morita equivalents. They were there. And they have geometric significance. One thing which I should add, in fact, which is related to the talk of Paul Baum tomorrow, is that in 1980, I went to a conference. That conference was in Kingston. And in Kingston, I explained what I had found in this contrandu note. And by the way, Tomita was there. Which was a great occasion to meet him. And what happened was the following. By constructing these projective modules, I had in fact constructed K-theory classes. So in fact, what I had shown is that a transversal to a foliation gives you a K-theory class. That was a general nonsense fact, okay? But of course, I had no idea at all of how one should get possibly all K-theory classes. And I had the incredible chance to meet Paul Baum and to listen to his talk. And Paul Baum had devised with Douglas, what he had devised what they called MEF. These MEFs were maps from some other manifold, you know, with some more structure, a bundle and so on, to a given manifold. And with that, they were constructing stuff. And then I realized immediately that this was giving the way, because a transversal is just an étale map from a manifold to the space of leaves. But you can imagine many other maps to the space of leaves from another manifold. And in order to map to the space of leaves, you don't have to map to the ambient manifold. You have to, you can map locally to the ambient manifold such that these maps agree on the space of leaves. And when you do that, you obtain the geometric groups that we defined with Paul Baum, and which led to our conjecture and so on and so forth. So in fact, you know, okay, this meeting was a meeting, by the way, in Kingston in 1980, organized by Jim Woods. And I mean, it had lots of repercussions because, well, I mean, at the time it was, you know, a meeting in person. And of course, the main part of the meeting was to try to kidnap somebody and talk, you know, in the corridor and so on and so forth. So that was the idea.
Okay, thank you very much.
Okay, another chance for the on-site audience. Well, if not, let me ask somebody from online. There are many more of you than us.
I see that there are might be some questions. Yeah, but I mean.
Oh, on chat. Oh, sorry. Yes.
On chat, yes. So let me look.
Is there a reduction from type 2 to type 1?
Sorry? No, of course not. No, no.
Quick answer.
No. No, I mean, let me answer the question in a better way. I mean, the theory of type 2 factors is a fantastically involved theory. It's a fantastically involved theory. I mean, it's a theory which, okay, in which, you know, there are incredibly great contributions from Voiculescu, Popa, Stefan Vass. I mean, you know, it's an amazing theory. I mean, it's where property T, for instance, is playing a crucial role. So I mean, it's by no means a trivial theory. It's a marvel of mathematics in a way. I mean, you know, the theory of type 2 factors, type 2-1 factors, really.
Okay.
Sorry, may I have just
go ahead, Adam.
So,
yes.
So for a canonical foliation, still there are some values of parameters which gives non-Morita equivalent algebras. Yes.
No, of course, no. But here I am looking at the Kronecker foliation with a fixed theta. Okay.
Okay. But still, if you take two different theta, it could happen that these algebras are not Morita equivalent. And
of course,
yes. And my question is the following:
yeah,
is it possible to see this from a classical point of view, not using algebras, but just looking on the space of leaves? On the foliation.
Well, but how do you look at the space of leaves? I mean,
exactly. So
how
it is
do you
not
look?
visible.
I mean, of course, I mean, you can do artificial things. I mean, you know, but I mean, obviously the right way is to take. I mean, you could take a topos theoretic point of view and so on. But I mean, all these points of view are local. The main point of non-commutative geometry is that it gives you a global point of view, and then it gives you global invariance. So I mean, you know, so this is the main difference.
Yes, so this was exactly the reason for asking this question, since classically it looks the same, just everything.
Yeah, sure.
Together,
I mean, they look the same. Sure. No, but I mean, yeah. There is one question which is, if you want, very non-trivial, related to the Kronecker foliation, which is the following: you can build something which has the same C-star algebra as the Kronecker foliation, but which has a different measure theory. What do? You take a diffeomorphism of the circle, which has the same theta as a Dangerois invariant, which is called the rotation number. Now, when you take theta to be a number which is not which is like a Liouville number, one can show, I mean, this follows from the work of Michel Herman and Yokos, one can show that in that way, by doing that and taking the foliation, which is obtained by the suspension of the diffeomorphism, you can get type 3 at the measure theory level. So this means if you want that the C-star algebra corresponding to the Kronecker foliation have very different smooth structures, and they are not classified. So, I mean, one of the great problems, if you want to have problems, I mean, after all, one of the great problems would be to classify smooth structures on the C-star algebra of the irrational rotation. I mean, there are several names which I should mention, I mean, related to the C-star algebra of the irrational rotation. I mean, Mark Riffel was the first with Bob Powers to construct a non-trivial idempotent. What I did was to transform this idempotent into a module, which was very analyzable. Pimsner and Voiculescu were the first ones to compute the K-theory of the C-star algebra of the irrational rotation. And this was a tremendous achievement. I mean, so I mean, these things exist, and okay, they all require a lot of work. And probably what I would say is that one of the keys in order to classify the smooth structure of non-commutative tores is to use the Schwarzian derivative. I mean, it should play an essential role. It does play a role in the work of Michel Herman, and it has meaning in non-commutative geometry, thanks to the work I did with Henri Moscovici.
Okay, thank you. Thank you very much.
All right. Anybody else? Masoud, how about you?
Well, yeah, thanks. I'm just enjoying the talk and Marvin.
I know.
all the beauty. Yeah. Yeah, thanks, Alain. This was fantastic. Yeah.
Yeah, well, I mean, one should remember these talks are really an introduction. I mean, they are really an introduction, and they are an introduction to the talk which I gave in the non-commutative geometry seminar. I mean, about spaces.
Yeah, it's a much needed introduction. Yeah.
Yeah.
So shall we have a 15-minute break?
Sure.
Maybe.
Well, I thought this was a break.
Oh, no, this was hard work.
I thought this was a break. I mean,
but we can continue if you want. I don't know.
No. I mean, in my course in the college, I used to, when there was no possibility to make a break, I used to take a joke. I used to tell a joke. So now I don't even dare. I say.
But can I ask?
Yeah, go ahead, Ludwig. Ludwig, welcome.
Hi, Alan. I just have a small question. In the case
can you show yourself, Ludwig?
Yeah. We don't see you, Ludwig.
Okay.
We don't see your face.
Face us.
Can you put your camera?
Yeah.
Now.
Okay, good.
So.
Okay, good.
In the case of type 3, you mentioned Hack and Kastler.
Yeah.
So what is the group of which you take cross product, and what is the
no. What I said about Hack-Kastler were for the Hack-Kastler axioms of algebraic quantum
local quantum field theory.
Local quantum field theory, yes, yeah. And there you have the work of Araki and Woods, which showed that you get type 3. In fact, you get type 3-1 as local.
But in particular case, I don't know in Minkowski spacetime. What would be the cross product?
No, this I don't know. No, in fact, they don't come naturally as cross products. They come naturally as ITPF1, as infinite tensor product of type 1. Okay. That's the way. Okay. I mean, they come naturally, if you want, as representation of Clifford algebra. So, I mean, it's ITPF1 stuff, yeah.
Okay. Thanks.
Okay. So maybe let's have a 15-minute break because we have coffee served here. So I know we cannot bring coffee to you guys online.
But then I will disappear and have tea, okay? In the meantime.
Yeah, exactly.
So we start at 15 past. Eh?
Exactly.
Okay,
perfect.
very good.
15 past. And I pause recording for 15 minutes. Okay, recording in progress, talk in progress. Let's continue. Alain, the floor is yours again.
Okay. So let me start the second talk by some philosophical idea, which is, sort of easier at the start. So somehow, before I explain the quantized calculus, I want to suggest one thing, which is that we are all attributing the variability, the change of things that we see and so on, to the passing of time. But my belief is that there is, in fact, a variability which is more primitive than that, and which is in the quantum. So, to illustrate that, I just want to show you some apparatus, some device, which had been, if you want, devised by some engineers in Switzerland, in Geneva, actually, and which is a generator of random numbers. So normally when you generate random numbers, if the attacker would really know what you are doing with the computer, well, they would be able to crack you. But however, these engineers, they have fabricated a device which nobody can crack, even if you would know completely what the device is and so on and so forth. And the reason is the following. The reason is that this device is quantum. So the way it works is that you have a light source, so it emits photons. And these photons, they go through a detector. And this detector is essentially something like that. What you have is you have photocells. And somehow, what we know from quantum mechanics is that the photon that passes through a very small slit of about the same wavelength, it will eat one of these photocells, but you cannot reproduce the experiment of making the photon eat the same photocell. This is impossible. It's impossible from the Heisenberg uncertainty principle, which means that in the quantum, there is, if you want, at every moment, there is a generation of randomness which is irreducible to anything that we know. And so, this to me is the perfect justification of replacing the notion of variable as we are used to think about it by the quantum notion of variable, which I repeat, is a self-adjoint operator in Hilbert space. Now, one of the great new virtues of this notion is that the discrete and the continuous begin to coexist. So the reason why in the ordinary framework, the discrete and the continuous do not coexist is the following: is that normally, when you take the notion of variable as being a map from a set X to the real numbers, okay, a real variable, then, okay, let me try to make a discrete variable coexist with a continuous one. Well, if I have a discrete variable, what do I mean by that? It has, a discrete set of values, and each of them is reached a finite number of times. So this implies, so if it is discrete, if you want, this immediately implies that the set X is countable. Okay, but if the set X is countable, well, you cannot have a continuous variable. Now, this difficulty, is totally eliminated by the quantum notion, because there is only one Hilbert space. So if you take the Hilbert space L2 of L2 function of 0, 1, it is the same as the Hilbert space little L2 of the integers. So in the same Hilbert space, you can have a continuous variable, which is a multiplication by X here in this space here. And you can have also a discrete variable, which is a multiplication by N in this. So why isn't there a contradiction? Because I showed you before that the discrete variable cannot, forces you to eliminate continuous variables. Well, the reason is the following. The reason is that these two variables, X and N here, they do not commute. So it's because they do not commute. If they would commute, then they would have a common spectral decomposition. And then the objection which was there would apply perfectly, but it doesn't. It doesn't because they don't commute. So if you want, what is amazing in the non-cumulative framework is that you have the coexistence of discrete and continuous, except that, okay, they cannot commute. So the non-commutativity is in fact a blessing. It's not a problem. It is a blessing. And I have explained many times, that in fact we are used to non-commutativity because of words, because of the way we write words, and so on and so forth. Now, there is another blessing with this notion of variable, which is coming from Newton's writing. In fact, if one looks at Newton's writing, one finds that there was a huge difference between the point of view of Newton and the point of view of Leibniz. Because when Newton was talking about infinitesimals, he was not talking about the numbers that would be infinitesimals. This is what Leibniz would have in mind. What Newton wrote, and when he was talking about infinitesimal, he was always talking about variables. Okay. And in fact, he was very precise. And there is a talk which is given by a Russian mathematician and philosopher, in which he explains what Newton had in mind. And what he says is that in a certain problem, this is what Newton had in mind. In a certain problem, a variable is a quantity that takes an infinite number of values, which are quite determined by this problem and are arranged in a definite order. And then he goes on, Newton goes on, a variable is called infinitesimal if among its particular values, one can be found such that this value itself and all following it are smaller in absolute value than an arbitrary given number. Now, the absolutely mind-blowing fact is that if you take on face value this definition of Newton, but if you use the quantum formalism of what is a variable, then when you translate the thought of Newton, you find exactly what is infinitesimal. And what you find is that the new setup, if you want, the quantum framework, has exactly the room which is needed to accommodate with the idea of Newton of what are infinitesimals. And what are they? Well, they are operators in inverse space, okay, which have the property of, if you want, being smaller than epsilon for any epsilon. But as Newton was writing it, namely that if you look at their characteristic values, which are the eigenvalues, so mu n, if you want, it is the nth eigenvalue of the absolute value of t, of absolute of t, okay? So if you look at these, well, they form a decreasing sequence, but this decreasing sequence should have exactly the properties that Newton was talking about, namely such that this value itself and all following ones are smaller in absolute value than any given number. So what that means, it means that the sequence of eigenvalues of the absolute value is tending to 0. These operators are well known as Hilbert space operators. They are called compact operators. And they have all the right algebraic properties that you could expect. That means when you add two compact operators, two infinitesimals, they are still infinitesimal. When you multiply an infinitesimal by a bounded quantity, by a bounded operator, it's still an infinitesimal. So they form a two-sided ideal. Whether you multiply it on the left or on the right, it doesn't matter. So, this is, if you want, the beginning of this calculus. It's the beginning of this calculus because in the quantized calculus, now the infinitesimal makes sense. So they make sense as compact operators. But if you would just have, the infinitesimals as compact operators, that wouldn't be enough. What you have is the order of infinitesimals. And to define the order of an infinitesimal, what you have is that an infinitesimal is of order alpha if the eigenvalues of its absolute values, and with these things, which I was talking about before, un of t, they decay, but they have to decay in a certain way. And for instance, for an infinitesimal of order 1, they have to decay like 1 over n. As we shall see, this will be a crucial ingredient in order to define the integral, to have the analog of the integral. At the moment, we don't look at the integral. We just look at the differential. So, this quantized calculus is really, if you want, at the origin of the paper which I wrote in the beginning of the 80s about non-commutative differential geometry, because it gives you the scene, if you want, the framework in which you just have to translate the ordinary notions, and then you can operate. And the differential of a variable is obtained by the commutator of an operator with the operator f, which is essentially unique in inverse space, up to equivalence, which satisfies f squared equals 1, which is self-adjoint. So it has only two eigenspaces for the eigenvalue +1 and -1. And the fact that this operator satisfies this condition that f squared equals 1 tells you that when you take the differential and if you iterate the differential twice, you get 0. And the reason is the following. The reason is that, well, in general, you define differential forms by this type of expression, where the differential of a function, or if you want, of an element is defined by the commutator. But in general, when you take a form of degree k, its differential will be obtained like this. The differential of omega will be given by the commutator with f, but it will be a graded commutator, where the plus or minus will depend on the degree of the form. So for a form of degree 1, for instance, it will be f omega plus omega f. And if omega is already of the form f commutator f, what you check, because f squared is 1, is that this will give you 0. So the square of the differential gives you 0. Okay. And since the square of the differential gives you 0, and you can also multiply the differential forms together, when you look at this calculus, if you want, with these differential forms, what you find is you have what mathematicians call a differential graded algebra, a DGA, differential graded algebra. Okay, and then with a little bit more effort, of course, I mean, this is a very abstract thing. Here you have very concrete ones. And with a little more effort, you can, using the trace, okay? Well, in the case when the degree is even, you have to use what is called the Z2 grading, okay? And all of this framework is in fact traced back to a paper of Michael Atiyah, which goes back to the, I think, 68, and which is called abstract elliptic operators. So, I mean, this will be the link if you want with the previous stuff. But, I mean, what happens is that when you have the abstract elliptic operator in the sense of Atiyah, you have the F, and you can do all these calculations. And in the even case, you have a grading, a Z2 grading. And then what you find out, just by doing this very simple manipulation with the trace, using the trace, well, you find you are forced into a theory which is the cyclic cohomology. So I should say that you know, there will be a conference held by the Fields Institute this year in September, and I mean it will be online, and I mean this will mark the 40th anniversary of the talk which I gave in Oberwolfach about cyclic cohomology. Now, this cyclic cohomology seems mysterious if you don't know that it's coming from the quantized calculus. But when you start with the quantized calculus, okay, what do you get? Well, what you find out is that out of an F and an algebra, so if you have an abstract elliptic operator in the sense of Atiyah, what you have an algebra which is represented in Hilbert space, and you have this F of the quantized calculus. Okay. Now, out of it, you get this DGA that I was explaining. You get this differential graded algebra. And then what you find out is that with this differential graded algebra, you can compute what is called the index map, which goes from the K-theory of A, we shall come back to that later, from the K-theory of A to the integers. And I mean, one instance, the most primitive instance of that was the case that I explained before of the non-commutative torus and of the fact that I was getting an integer when I was computing the integral curvature. It is a special case of this construction. Now, this construction, what do? You do exactly what I was explaining before. You take the differential form and so on. And then what you want to do, you want to use the trace of the differential form. So you want essentially something like this. You want to use, if you want, the trace of the differential form in order to write expressions, typically an expression like the trace, if you want, of projection you put the gamma here, and you put the F commutator E to some power, the right power, and that would give you the index. That would give you the index of the k-homology cycle defined by Atiyah with coefficients in the projection, which is a K0 class. Now, what happens is that, what you find out is that this n should be large enough, because in general, what will happen is that the commutator, the differential of the element of the algebra, so the d slash of f, if you want, which is a commutator with f, will be an infinitesimal. But this infinitesimal will not, in general, be small enough to be trace class. And in order to make it trace class, you have to put enough of them, because of course, when you make products of infinitesimal of order 1, for instance, of a lesser order, then you will get something which is an order so that you can take the trace, that you can sum the eigenvalues. So this n has to be large enough. Moreover, this n, you cannot move it by 1 to make it large enough. You have to move it by 2. Why? Because there is parity involved. In the odd case, you have to use something like you start this slash u and you have to put enough of them. In the even case, you have to use something like what I put here. So you have to use something like here. So you have to respect the parity. Now, because of this parity, what was very obvious to me from the start is that the cocycle that was assigned to an n, which was like phi n, there should be a relation between this cocycle and phi n plus 2, which of course will exist if phi n exists. And in that way, I discovered a very strange map from these cocycles, which I call the map S, and which was, if you want, going from a group which I was calling the cyclic homology group HCN to HCN plus 2. So the properties, if you want, of these characters of these, of these differential grade algebras, this led to cyclic homology, but it led immediately to a periodicity map, which is called the map S. And there was another thing, which was also very important, which was that the cohomological property of the integral, in fact, could be weakened, and then they were related to a known theory, which is called Hochschild cohomology of the algebra A. Okay, which was a known theory, Hochschild cohomology of the algebra A, and which is in fact more precisely the cohomology of A with coefficients in the dual of it, because Hochschild cohomology is defined for coefficients with a bimodule. Okay, and then this thing sort of assembled together by miracle, and they gave something which was purely algebraic, which didn't need the quantized calculus, and which I call cyclic cohomology, and which is the following, which is that if you have an algebra, you can define something which will replace the Dirac theorem. But the big thing, because it was known, there were known theorems, before about the Dirac theory in the commutative case. But here the main point was that the Dirac theory extends to the non-commutative case. Okay, and it extended, with lots and lots and lots of examples. And the key finding of that time, which I announced in Nobel Alpha, was a long exact sequence. And this long exact sequence is relating the Hochschild cohomology, which is computable, okay, to the new theory, which is called cyclic homology. And the way it's all geometric what happens, because what happens is that if you have a Hochschild cocycle, you don't have something like a closed cycle in the sense of differential grade algebras, but you can take its boundary. And this boundary gives you a certain operator, capital B, which in fact plays the role of the Dirac boundary, and which goes into something of dimension 1 less. But then by this strange, very strange map of periodicity, which I had found, which was dictated by the quantized calculus, then you go from n-1 to n+1, and it continues like this. And you get a long exact sequence. And with this long exact sequence, you can really compute, of course. You find very easily, this is not a big thing, that in the case of smooth functions on a manifold, so if you take the algebra A to be smooth functions on a manifold, you recover the RAM. So this gives you back the RAM. This is not a big deal. Okay. what was a big deal really is that what happens when you do this for the smooth functions of non-commutative tools. Okay. Well, what you do is much more delicate. And what you find out is that the periodic cyclic homology, in fact, gives you exactly what you would expect. It would give you the same type of Dirac as for the ordinary torus, but the intermediate calculation with the Hochschild cohomology and so on depends on the Diophantine nature of theta. So if you want, okay, it was clear at this point, and this is what I wrote in the papers on non-commutative differential geometry, that the Dirac theory was extended. And so one of the fundamental tools of ordinary differential geometry. And when, a long time before, when I was talking to you about this, the previous talk, when I was talking to you about this, this thing here, this God-Bienvey, I mean, those things, of course, only make sense because they are cyclicocycles. They wouldn't make any sense if you didn't have a theory, which is cyclic homology, which allows you to define the transverse fundamental class, to define contraction by a vector field, and so on and so forth. So all of these things now make sense in the non-commutative framework. And okay, so if you want, one of the main kind of tools, okay, which are the differential geometric tools of the Dirac theory. But of course, this is not the end. One obtained from that, when you formulate it in more modern terms, I mean, there is a spectral sequence, there is a bicomplex, and okay, and many properties of this bicomplex are crucial in the development of the theory. And the theory was independently discovered by Tsigan, I think in 1982 or something like that. And he used it, as an understanding of additive case theory. And of course, I mean, we put all our efforts together. And but the quantized calculus has many other aspects. And I want to show you one aspect which is still under study. I mean, and which has to do with differentiation and with things that, that you could absolutely not do if you were using the ordinary distributions and ordinary calculus. And for that, I will take a very concrete example of the quantized calculus, which is the quantized calculus for functions on the circle or functions on the real line, if you want. So, but I think of the real line as being P1 of R. Okay, the visible part of P1 of R. And so it's equivalent to the circle, if you want, to S1. And on the real line, the Hilbert transform, which is at the root of the quantized calculus, has a very simple form. It is given by what is called the Hilbert transform. Now, as the Schwarz kernel, it's represented by the following. So when you take the commutator, the differential of the quantized differential of a function, what you get something which on the diagonal will be the derivative of the function if the function is smooth, but which will continue to make sense when the function is not smooth at all. And it will be given by f of s minus f of t over s minus t. It's a finite difference quotient, okay? So this is the quantized differential if you want a function. Now, you can easily prove that if the function on the real line is in Schwarz space, then its differential is in fact an infinitesimal or infinite order. You can also prove that this quantized calculus is invariant under conformal transformations. So you can transport it immediately to the circle. You can go back and forth to the circle. In fact, you can go to any domain in the complex plane. Now, so what happens is the following. What happens is that now I want to use this quantized calculus in a completely different way. And for that, I need a new tool, which is integration, which so far I didn't mention. Now, we all think that we understand integration because we read in books or many books, you write integral of f of x, dmu of x, okay? And so, the integration is defined just as defining the measure, which measure you are talking about. And okay, of course, then you can think that you understand integration. But here we shall understand integration in a completely different manner. And I mean, I have told this story many times. I mean, it is thanks to a meeting with Dixmier that I found that, in fact, Dixmier had found the correct way to integrate in non-commutative geometry, but he had found this in the 1960s. I don't know exactly the date when Dixmier found this. And I mean, Dixmier, of course, was not motivated by integration in non-commutative geometry, but he was motivated by finding a trace. So what Dixmier was trying to find, he was trying to find a trace on operators in Hilbert space. Okay, trace on operators that would be different, that would not be the ordinary trace, the usual trace. Okay. And I mean, Dixmier found it, but I mean, interpreting his result in terms of the quantized calculus, what Dixmier had found a trace, which is a great property, I mean, to have a trace when you want to integrate. But he had constructed, using the amenability of the expert group, he had constructed a trace which had the property that, if you want, if I call this trace like this, like an integral with a bar, it had the property that the integral of an infinitesimal alpha is equal to 0 if alpha is of order bigger than 1. And you know, this is exactly what you want if you want to do calculus. Because when you want to do calculus, you want to be able to simplify under the integral sign by anything which is of higher order. Or if you want, what I believe is that it is through this integral that we perceive the external world, that we sort of wipe out all the quantum details which are irrelevant for a classical view of things. So the way Dixmier found this integral, he found it, and in fact, it will integrate, if you want, the infinitesimals of order 1. So the integral of Dixmier will be defined when omega is of order 1. If omega is of order 1, and what does it mean that omega is of order 1 from what I told you before? Let's say omega is positive. It means that its eigenvalues are of the order of 1 over n. But if the eigenvalues are of the order of 1 over n, I cannot take the sum of the eigenvalues. I can take the sum of the lambda n because they are of the order of 1 over n. It's divergent. And what Dixmier had found, he had found a way to extract the coefficient of the log divergence. When you take such a sum from, let us say, 1 to big lambda, well, it will behave like, you know, some coefficient times log of lambda. And Dixmier had been able to extract the coefficient A in a way which was invariant. Of course, it involved a choice, and we shall see that this choice plays a role. But what happens is that when you do a little bit of quantum field theory, what you find out is that these logarithmic divergences are everywhere in the place, and from operators. And so, I mean, thanks to Dixmier, to the work of Dixmier, I was able to give a meaning to the integral sign independently of the measure itself. So instead of having, if you want, this whole package in one go, which was given by all these things, I mean, by this thing and that thing all together. Now, the integral sign makes sense by itself, completely by itself. And I mean, I'm gradually, you know, getting more and more convinced. I mean, of course, there are more and more works on that, which I will present very soon by other people. And I mean, but I'm more and more convinced that all of the integrals we know, they are much better understood when they are put in this form. Now, one of the things that, I had, if you want, I had sort of understood partly at the time was that, okay, one could, thanks to this new integral, one could do things that would never be able to do with distributions. And so a typical example is you take a Julia set and you take the Riemann mapping. So this Julia set is a Jordan curve. It doesn't look like that, but it's a Jordan curve. And so there is a Riemann mapping which goes from the unit disk to the inside of the joint curve. But of course, that function Z is extremely irregular when you look at its boundary values. But it makes sense, okay? It's extremely irregular. But even though it's extremely irregular, and even though, I mean, you could take its differential in the sense of distribution, but you could never, absolutely never, take the absolute value of this differential and raise it to the power P, where P is the Hausdorff dimension of the Julian set. Okay, and I mean, what I had sort of guessed, in that sketch of proof in my book, was that when you take such an integral, you get something which is, in fact, the conformal measure. And I mean, with Fedor Sukhoshev and Dima Zanin, in fact, we first treated the case of quasi-Fuchsian groups, which I'd also put in my book. But then with McDonald, Sukhoshev, and Zanin, we were actually able to put on solid ground the work which I had sort of started, if you want, in my book. And I mean, it's a lot of work. Technically speaking, all these things are extremely difficult. But I mean, on the other hand, they are very easy to write down. And I mean, what is, if you want, the very surprising fact, and there is in fact, a book which is written by Lord, Sukhoshev, and Zanin. They had written a book on singular trace, but now they have another version of the book, and I wrote the back, explanations about it. And I mean, it's amazing that the more one studies the singular traces, the more, they show amazing feature. And there is a recent paper by Raphael Ponge, which is very interesting, which is on arXiv, and in which he goes precisely in the direction that I was alluding to, which is, if you want to understand better and better, that for most of the cases that we know, not all, of course, and each will be a more difficult work, it's really like integrability of something. Namely, in the Dixmuir trace, there is a choice which is involved, or in the singular traces, you do have a choice which is involved. But in fact, in the good cases, in most of the cases that we know, actually, this choice is relevant because there is a convergence, if you want, which happens. And this convergence is very much like, if you want, the convergence of the Riemann sums or something like that. I mean, it's something which is intrinsically fundamental in the integration process. Now, it turns out that all these developments and so on is related to a fundamental discovery of Wojcicki, well, which of course was later than Dixmuir, but which played an essential role, of course, also in the relation with the Dixmuir trace, and which is the Wojcicki residue. So what Wojcicki found, he found something which is amazing, which is that when you consider the algebra of pseudo-differential operators on a manifold of arbitrary order, on a manifold M, then, of course, you could say that you can integrate, you can take the trace of operators of sufficiently low order and so on. No, what Marius Wojcicki found is that there is a formula, an explicit formula, which is using the integral of the symbol of order exactly minus n, where n is the dimension of the manifold, but which extends to a trace on all pseudo-differential operators. And I mean, with respect to the previous discussion of the quantized calculus, this is absolutely amazing because it gives a way which is related to analytic continuation that not only, I mean, so as I said, when you integrate an infinitesimal, integral of omega will be equal to 0 if the order of omega is bigger than 1. Okay. Now, and normally what you would integrate are the infinitesimal of order 1. So normally the ones which are interesting, which are natural to integrate, are order of omega is equal to 1, okay, because of the logarithmic divergence. But what Marius found is that at least in a very specific and very sort of a remarkable case, that case of pseudo-differential operators of manifold, in fact, you can integrate infinitesimals which are not of order 1, but which are of lower order. That's mind-blowing. And in particular, you can do something which normally you never be able to do. You can take a manifold of dimension 4, and you can take the integral of ds2. Now, I don't have time to explain that in non-commutative geometry, the ds is given by the inverse of the Dirac operator. So it is the Dirac propagator. But if you want to understand that, you can listen to the talk which I gave last Friday, and for which this one is an introduction. But what happens is the following, is that thanks to the Wojcicki residue, you can write this expression and wonder what it is. And if you think a bit, you will find out that it has to be the Einstein action. And so I suggested to, in fact, to Daniel Kastler, and then Kalau and Valls also proved it independently, that in fact one should find the scalar curvature, the integral of the scalar curvature on a manifold of dimension 4, exactly by doing this operation of integrating, if you want, the by the Dirichlet trace, okay, this ds square. Okay, now in fact, this discovery of Wojcicki, which is an extension of, if you want, the Dirichlet trace, allowed us, with Henri Moscovici in our work, to improve considerably on the type of index formula which follows from the quantized calculus. If you want, when you write down the quantized calculus, you find, let me show you, sorry, you find a cyclical cycle which is associated to the k-homology class. So of course, you know, after Atiyah, k-homology was considerably developed by Kasparov, by Brown-Douglas-Fillmore, and I mean, all of this enters into play in the general theory. But okay, what I found, if you want, is that there was a Chern character in k-homology that was allowing to compute the index pairing. But the formula which I had found in my IHES paper on non-commutative differential geometry was a very non-local formula. And in our work with Henri Moscovici, what we found with the use of the Wojcicki residue is that it was possible to write in a rather wide generality a formula which was giving you the full character, and which, if you want, at the top degree, when you write this formula, it is given at the top degree by a Dirichlet trace, okay? So at the top degree, it's given by something like that, that you take A0, you take the commutators with D, A1 up to DAN. So this is actually a Hochschild cycle. And, if you want this formula here, which was using the Dirichlet trace, was only giving you, in the log XBI exact sequence, it was only giving you the image of the Chern character by the map from the cyclic homology to the Hochschild homology. So it was only a partial information. And I mean, with Henri, we succeeded to have the full formula, which is a formula which essentially, if you want, gives you what is the analog in non-commutative geometry of the Plantré-Huggin classes. And I mean, in fact, of course, with Henri, we investigated in a very broad sense what was the non-commutative geometry of foliations, of the transverse geometry of foliations, which is, if you want, the wide class of example I was talking before. And what we have found with Henri is that, if you want, in the transverse geometry of foliations, which we studied for many years, in fact, this transverse geometry of foliations, the same idea as the idea of Takezaki, which, you know, after I had done the 3 lambda, except for type C1, Takezaki found a way to unify what I had done by duality. But with Henri, what we found is that this duality of Takezaki could be applied to foliations, and that there was a way to apply this duality to foliations, which was, if you want, reducing foliations which are very, very complicated type 3 to the type 2. But not only at the level of the measure, not only at the level of the factor, but at the full level of the geometry. And what you get when you do that, I mean, instead of the, you know, in the theory for factors, you get a cross product by R. Now, in the theory of foliations, you essentially get a product by by something which is like the quotient of GLNR by the maximal compact, and so on. So, I mean, you get something which is much more fancy, but what it does, it reduces, if you want, the transverse geometry of foliations to the type 2 situation. And this type 2 situation is almost isometric. And it turns out that then, using the hypoelliptic theory of Ormander and so on, then one is exactly in the right framework for non-commutative geometry, which is to have everything formulated in terms of operators. So the situation is like this, if you want. So this is the thing which I showed before. So the situation is that, as I explained, you know, the Dirac homology of manifold has been replaced by periodic cyclic cohomology. The Atiyah-Singer has a perfect analog, which is the local index formula in commutative geometry. But then it turned out that when we were working with Henri, we wanted to find, you know, this formula in the case of foliations, and we were led to a new type of cyclic homology, which is cyclic homology of algebra. And that turns out, this theory, if you want, turns out to be a wide generalization of Lie algebra cohomology and of characteristic classes. So there is, again, if you want, an extension of the kind of commutative tools that we know. And somehow, I mean, this is just the beginning, if you want, of a very, very dense dictionary, which translates from the classical language to the quantized calculus, to the language of non-commutative geometry. And I mean, each of the lines, of course, I mean, the first line, real variable go to self-adjoint. I mean, this goes back to von Neumann. The range is a spectrum, we know that. One amazing fact, as I said, is that, you know, when you take a self-adjoint operator, you can apply it to it any measurable function, which fits very well with the idea that they are variables. Then, okay, you have this, you have the compact, of course, which are infinitesimal, you have infinitesimal order alpha. Okay, you have the integral. The integral was much more costly than other things. And then geometry is coming. And geometry is coming from the line element. It's coming from, if you want, thinking around Riemann's idea of what is geometry. And I mean, just to have a relaxed ending, I will go through something which really, I mean, for me, is extremely meaningful. And this is the following. I mean, it is the fact that there is a change of paradigm. When you go from ordinary Riemannian geometry, where the ds square is given by g mu dx mu dx mu, to the non-commutative geometric framework, where the ds is a fermion propagator. It is the inverse of the Dirac operator. Okay. Now, when you go from this to that, you think that you are doing something extraordinary. But in fact, so I mean, it's not so extraordinary in the sense that you can still measure distances. The distances are measured not by, you know, taking an arc between 2 points and trying to make it as short as you can. No, what you do is you have these 2 points, and what you do is sending a wave. Okay? But you send a wave which has a frequency which is limited, and then you count the phase shift. This is what gives you the distance. Now, I want to finish by something relaxing, which I love to say, even though I stated it many times, but it doesn't matter because, as I said, I want to convey some mental picture. I want to convey some ideas, not formulas. And I mean, the idea which I want to convey is that, so as I said, you know, when you do this shift from the classical language of ds square of Riemann and so on, to the new paradigm where you have the fermion propagator, you think you are doing a tremendous step. But in fact, this step had been taken. I will come back to that later. This step had been taken. And how had it been taken? Well, it had been taken as follows. You see, I mean, back in the French Revolution, the people were, I mean, they were very intelligent and sort of, you know, intellectuals, and they try to unify the metric system. And the reason why they try to unify it is that if you look back, I mean, there are books about that, you will find out that, I mean, there were like 1,000 different definitions of the unit of length in different towns. So, I mean, for instance, if you were selling tissue, you had to adapt to every city and so on. And so, I mean, they try to unify the measurement of length. And I mean, so there were great scientists at the time. And finally, they came up with the idea that, okay, they should define the unit of length as a certain portion of the circumference of the Earth. Of course, you wouldn't go to the pole to measure, or to the equator and so on. What you would do is take fixed angles from stars. So they took a fixed angle from stars, and the fixed angle was coming from two places. One was Dunkirk here, and one was Barcelona. And since you knew the angle from pointing to stars, okay, I mean, you just had to measure very carefully this distance. And then, okay, they had the idea that after measuring very carefully this distance, which was a real adventure by Delambre and Méchain, then they tried to specify their unit of length as being a platinum bar, okay, which was deposited near Paris. And it was a platinum bar. And I mean, this was, if you want, their way of thinking. It was very classical, because somehow, you know, the idea was that, okay, if you want to measure the distance between 2 points, I mean, of course, I mean, you wouldn't take the bar which was near Paris, you would replicate it, and you would count how many of these bars you have to put, you know, to go from point A to point B, and this would give you the distance, okay? I mean, this was the idea, roughly, okay? Now, what was discovered about the same time as the discovery of Heisenberg, which is amazing, is that in fact, this was not a good idea. And what I insist on, you know, is that the step which was taken to improve the unit of length at that point is exactly the step which is taken in non-commutative geometry, to pass from the usual paradigm to the new paradigm of the Dirac propagator. In fact, what was found in around the same time as Heisenberg was that, you know, this platinum bar, which was near Paris, okay, I mean, he didn't have a fixed length, which is quite bad, I mean, for a unit of length. And how did they find it? They found it by comparing the length with the krypton wavelengths, and they found that this was changing, actually. So, after a long time, the physicists were really smart people, realized that, okay, this was out of the way. I mean, this was not a good definition of the unit of length at all. And they should replace it by the measurement, by the instrument by which they had been able to find that this platinum bar was changing length. And what was this instrument? It was actually a wavelength. And at first they took the wavelengths of some transition of the krypton, but after much thinking, they found that there was a better one, which was the wavelength corresponding to a hyperfine splitting of the cation. The reason why it's hyperfine is that hyperfine means, if you want, that the difference between the frequencies would be very small, and that will give you a large wavelength. And in fact, the wavelengths that you get by this hyperfine splitting is something of the order of 3 centimeters. So it's like the type of wavelengths that you get in a microwave. And I mean, for that reason, now one can make instruments to measure distances, which measure distances up to 10 decimal places, and which are based on this cation, and which are sold in a shop. So you can buy in a shop an instrument which is based on that, it's not based on this platinum bar, and which measures distances with incredible precision. Now, so I mean, this improvement, this of course induced, so these are the hyperfine splitting, the transitions that correspond to that. But what I insist on is that if you want the sort of baby step or fundamental step of non-commutative geometry in the sense of geometry, namely in the sense that now you are going to do really geometry by measuring distances and so on and so forth, is precisely taken by this step of the new way of measuring distances, which is done by operators. Now, so to conclude, and the non-commutative geometry is a topic which has been developed by many people, which is related to all sorts of topics. I mean, one topic which played a crucial role is Kasparov bivariant case theory. I mean, it's, as I said, I mean, it sort of came from operator algebras, but I mean, it's related to geometric topology, it's related to differential and spectral geometry. It's of course related to high energy physics. And I mean, if you want to know more about that, besides the talk which I gave last week on Friday, there is a quite important talk which I gave last year in Harvard, where I explain in great detail, I mean, all the interplay with high energy physics and the understanding that somehow this framework of non-commutative geometry turns out extremely surprising to be suitable for space-time, I mean, in the Euclidean framework. And finally, it is also related, quite importantly, to a number theory. And for that, the talk which I gave last Friday, which is available on the website of the non-commutative geometry. So if you go to the blog, so the non-commutative geometry blog, which is on internet, I mean, you just put non-commutative geometry blog, you will get there. Then if you click, you'll get the talk which I gave, and which, I mean, applies if you want non-commutative geometry to these two topics. Okay, so I think I will end here, and I hope I have conveyed to you, some feeling, some wish to understand more, about these spaces which are so interesting and which are not static. Okay, thanks a lot. Thank you.
Thank you very much, Alain. Let's thank our speaker. Your talk would be titled "The Emergence of Non-Commutative Geometry." You really showed it to us how it emerged, and
yes,
I thoroughly enjoyed it. So let's continue with some questions. Adam, can we count on you?
Yes, I have another question, quite general, in fact. So I would like to ask you, what is your perspective on the right notion of morphisms between non-commutative spaces?
That's an excellent question, and there is a lot of work there. There is a lot of work. You see, there is a guiding principle in non-commutative geometry, which comes from K-homology. And since K-homology has been, thanks to Kasparov, transformed into a bivariant theory, it turns out that there is a guiding principle. Let me stop sharing. Can you see me better now?
Yes.
Yes. Yes. So what
yes.
I want to say, no, I don't think one sees me. I think one sees you, Piotr.
No, we see you on the screen. We see you.
Oh, you can see me? Yes.
Yeah, because that's the speaker. So whoever speaks is visible.
Okay, very good. Yes. So I mean, this is an ongoing topic. I mean, two of my students, I mean, were students at the time, Jules and Baj, have developed unbounded version of the Kasparov theory. Because if you want, one needs to understand that the fact that the paradigm of non-commutative geometry is that of spectral triple, where the operator D is not bounded, it's very important because if you want, it is the unboundedness of the operator, if you want the fact that its inverse is an infinitesimal, that allows you to consider its inverse as a line element. And it is thanks to that that you can do geometry. So somehow, if you want, the K-homological content of this is in fact encapsulated by the phase of the operator. And the phase is bounded. The phase wouldn't give you the geometry. So passing from the bounded to the unbounded is really the key step, which allows you to do the geometry. And in fact, this is very interesting because after the paper of Atiyah on the abstract elliptic operator, there was a paper by Isadore Singer in 1970, and Singer was advocating the unbounded. Which is amazing. I mean, so somehow, in fact, I have written a little piece for the as a tribute to Singer, which will appear in the notices, and in which I explain my encounter with Singer and how we discussed together and so on. So, I mean, behind the scene, in the paradigm of non-commutative geometry, there is this fact that it's not k-homology, which is important. It is the fact that you realize it by a very specific unbounded operator. So now comes the answer to your question. So the answer to your question is that, so Baj and Julg have transformed, if you want, the Kasparov theory, which is with bounded operators, into a theory where you have unbounded operators. You have unbounded KK classes and so on. And but they only considered it up to homotopy, namely by the type of k-homology class that they define. Now, there is a lot of ongoing work. And I mean, I don't want to give names because I would not be exhaustive. But there is a lot of ongoing work on developing morphisms between non-commutative geometry using unbounded KK cycles. And I think this is an extremely good idea, except that what you find out is that the cup product of Kasparov is not at all easy to do in the unbounded situation. And I mean, so far, if you want, there is nothing that I find totally convincing. But somehow, how to say it? I mean, if you want, what is in the background is the idea in geometry, in algebraic geometry, of what are called correspondences. Namely, if you take two, if you want to define a map in algebraic geometry from one space to another, you could think just of a plane map, but that wouldn't really do the job when you are looking at fancy situations and like the Frobenius and so on. And what you have to do, you have to replace it by what algebraic geometers called correspondences. Now, in a very funny way, I mean, I developed correspondences for factors. And I mean, it turns out that they are extremely efficient also in that framework. So, I mean, the idea here for non-commutative geometries is to develop the correct idea of correspondences, but it will have a lot of geometric content. The idea is that, you know, and one, well, okay, people love categories and all that, you know, but I mean, the difficulty is much more geometric and much more interesting than to develop an abstract category. I mean, you could develop 1,000 abstract categories without reaching the right concept somehow. But it is one of the key questions, the questions you ask. Yes, certainly, yes. One has, of course, pretty good examples. I mean, you know, like, okay, Morita equivalence, for instance, is a morphism, you know, of course, you know, typically.
Okay, so there is an agreement that for an isomorphism, it should be Morita equivalence, yes? Yeah,
well, no, an isomorphism should be a true isomorphism. Then, okay, then you have Morita equivalence. No, you shouldn't confuse the two. No, it's not the same. I mean, you know, and so on and so forth. Yeah. I mean, what is nice about Morita equivalence, let me tell you what is nice about Morita equivalence with respect to spectral triples. What is really nice about Morita equivalence for spectral triples, and this is a joint work that we did with Walter and Ali Shamseddin, I mean, is the fact that when you consider self-Morita equivalence of a spectral triple, you get the gauge bosons. So, I mean, okay, you know, this is kind of, this is really amazing. I mean, this tells you that, you know, the non-commutative framework is perfectly coherent. I mean, you look at just self-equivalence, self-Morita equivalences of a non-commutative space to itself, and you get the gauge theories of physics.
Okay, and since you mentioned this gauge theory, I cannot resist to ask another question. So, do you have some explanation for the number of generations in the standard model?
No. I mean, no. I mean, but I have a conjecture. Okay, but don't. I have a problem if you want. Okay. So okay. So the conjecture is the following. I can explain this very carefully. You see, when I say that the fundamental class of a non-commutative manifold is given by the Dirac operator and so on and so forth. Okay, I am not taking into account the fundamental group. Now, it turns out that, in fact, for non-simply connected manifolds, the k-homology, which is really relevant for the Novikov conjecture and such things, involves the fundamental group of the manifold. And then what does it mean? It means that you shouldn't consider the Dirac operator on the manifold itself, but you should consider the Dirac operator on the universal cover of the manifold. Now, when you look at it in examples, you find exactly what happens for generations. Namely, what you find out is that, for instance, if I would have a fundamental group, that would be the group with 3 elements, commutative. Then I would take characters of this group, and I would obtain 3 generations. Because it would correspond exactly to, if you want, having replicas of the Dirac operator, but twisting it when you twist it by a character. So there, the idea for generation would be obvious. I mean, it would be that we don't really understand what is at the local level the fundamental group of space-time. It could be a quantum group. It could be something that I don't know. And, you know, and then, okay, it would give you that the correct thing is not the Dirac operator downstairs. No, it is the Dirac operator upstairs. And that Dirac operator will provide you with replicas of the naive, you know, like first generation and so on. And of course, I mean, you know, this, okay, I mean, of course, one would have to work it out. And I mean, but there is a very, very enticing stuff to work it out, which is that when you look at the masses, the Yukawa coupling masses of the fermions, they appear as the Dirac operator for the finite space that you input, you know, in the standard model, the geometry of the finite space. Now, it turns out that obviously these Yukawa couplings, they have a kind of geometric behavior in the sense that they are like powers. They are not, you know, like an arithmetic progression. They are like a geometric progression. And that, of course, is very reminiscent of the Q of quantum groups and so on. So, I mean, you know, I'm just giving you a vague idea. Of course, it has to be worked out, you know.
Okay,
but
so
if you work it out, you get a big reward.
so this would require to define a fundamental group in the context of non-commutative geometry.
Yes, yes, there are attempts to do that, but they didn't convince me. I mean, you know, because of course it should be a quantum group. It cannot be an ordinary group. I mean, you know, I mean, the quantum groups are exactly the Lie groups in the non-commutative geometry framework. I mean, you know, and of course, I mean, where you have Stanislas Voronovich who made fantastic work on quantum groups. So, I mean, okay, you are ready to, to use it. And I mean, but then it's a lot of guesswork. You know, the strange thing about physics is that, okay, you have to do a lot of guesswork, and but there, the data is there. I mean, the data is given, is handed to you by the Yukawa coupling raised to unification. You have to run it to unification scale if you want it to be meaningful. So you have to take the Yukawa coupling, run it to unification, and then just stop, go for a trip where nobody is worrying you, no email, nothing, just think, you know. Just stare at it and think, okay? That's the idea.
Okay, thank you. Thank you very much.
Right, anybody from the Zoom, folks?
So the fundamental group for non-commutative tori or even irrational rotation algebra is not, there's nothing convincing either for that fundamental example.
No, I wouldn't say for that. No, that one should be a relatively easy case. I mean, because after all, it's a deformation of something for which we know. So, I mean, this is not the problem. No, the problem, if you want, is more to find a construction that sort of hands you an off algebra which is neither commutative nor co-commutative. In the attempts which I know, which are good, I mean, you know, but one forces commutativity somehow, artificially, by taking the center of something. And okay, I mean, this works, of course, in the commutative case, but you know, the sort of a rule of non-commutative geometry is that it should never, I mean, the criterion that it gives you the old result in the commutative case is by no means a good criterion, because if you would do that, you would never discover that you have a time evolution for non-commutative spaces, which is, you know, the starting point somehow of the whole story.
That's correct.
Anybody else? Yeah, I remember, Alain, I think it's at the beginning of your book that you wrote that generalization to non-commutative geometry is almost never straightforward.
Yeah, Yeah.
Right. And I fully subscribe to this point of view. It's
Yeah.
just every step. I think the exceptions maybe just projective modules and vector bundles.
Yeah, exactly. I mean, the extension is never straightforward. And I mean, I have to tell you one story. There is one slide which I didn't show, which was Penrose tilings, which is that there was a guy, and Penrose, I mean, you know, he was amazing because, I mean, back in, I think it was in 1987 or something like that, I was with him in a conference which was in near Munich in a castle, and Schloss Rheinberg near Munich. And I mean, Penrose gave a talk. And what he was doing, it was amazing because he was showing his Penrose tilings, and he had fabricated slides where he was showing two tilings that were looking almost the same, but were different. Now, this is exactly, and of course, I mean, after his talk, and he was saying there is something quantum there. And after his talk, I told him, yes, of course, because I mean, the space of Penrose tiling is a non-commutative space. And I mean, this is one characteristic of non-commutative spaces, which is the same. It would be the same if you try to look at the leaves of a foliation. One characteristic of Penrose tilings is the following. There are infinitely many different Penrose tilings, and there are some which are, you know, symmetric under the five-fold symmetry, which is impossible for periodic tilings. So there are infinitely many of them, but you cannot distinguish them by a finite piece. In other words, if you hand me a Penrose tiling and you hand me a very large finite piece, okay, and you hand me another Penrose tiling, in that other one I can find the same finite piece infinitely many times. So this means, you know, this is crazy. This means that these things cannot be distinguished from each other by a finite piece. Okay, I mean, when you take numbers, they can, of course. And that's the reason why you cannot embed the non-commutative space into the reals. It's precisely that reason that makes it impossible. So there are spaces which are, you know, really something totally new. I mean, something, you know, really, and you have to appreciate that. You have really to get some kind of, you know, understanding, some kind of mental picture of that if you want to understand them.
Okay, anybody else? I don't see any volunteers. So let us thank Alain again for a really beautiful talk. This was
okay, thank you. Thank you, guys.
Alain, there are many comments you see in chat. Many thank you in chat. It will be also saved. You know, thank you for such a beautiful, inspiring talk. Thank you. I mean, it's all over. There are many, many of them.
Okay, okay. Yeah, so, maybe you should send them to me to.
I will. I mean, it's all being recorded. So since I mentioned the recording, it will be tomorrow available on YouTube at the Banach Center YouTube channel.
Yeah. Okay.
And the lecture of Paul Baum is exactly at the same time tomorrow. You mentioned it in your talk, so it's exactly the same time. So it's 1500 hours our time. So it's, I think 9 o'clock New York time, and it's exactly tomorrow. So Alain, thank you so much again for being with us and showing that non-commutative geometry can make impossible things possible. This was part of the message. Okay, thank you so much.
Yeah. Okay. Thank you.
See you later. Bye bye. All the best.
Bye bye.
Stop recording.